Hey guys, welcome to the first of our two videos for section 8.5. We're going to be looking at all the properties of logarithms and comparing them to the properties of exponents, and then looking at how we can apply those properties as well. There is a handout to print out before you watch the rest of this video, so please print that handout from Google Classroom before you resume the video. There will be some parts that aren't on the handout, so if you want, you could just use the back of the handout for the other notes, or you could set up your own note sheet with the section date and I can statement that you see on this slide. But either way, please make sure you print that handout and then resume the video as soon as you are ready. All right, so we're going to look at the properties of logarithms and we're going to compare them directly to the properties of exponents, because one of the things I want you to see is that each property of logarithms, for the most part, has a corresponding exponent rule that you already know. And a lot of this is just a rearrangement of those rules. So for example, for exponents, you learned long ago that a to the 0 equals 1. In other words, anything to the 0 power equals 1. Well, if you do a drop and switch with that to convert to logarithmic expression, you would have log base a of 1 equals 0. So anytime we take the log of 1 with any base, we end up with 0 as our result. And we saw this when we graphed these as well, because all logs have an x-intercept of 1. So now you're just seeing it in algebraic form. Similarly, for exponent rules, we know that anything raised to the first is that same thing. With logs, we can do the same drop and switch and realize that we have a log rule that log base a of a always equals 1. In a sense that log base a and the a itself are canceling each other out. With exponents, we can think of a to the log base a of m equaling m. And similarly, we could also think of log base a of a raised to the m power being equal to m. In other words, you can think about it as that exponent becomes the result when the log base a and a, in some sense, cancel each other out. That's not actually what they're doing, but it's sometimes how people think about it. Similarly, we know that e raised to the natural log of m equals m. And the same thing is true essentially in reverse, where if we think of the natural log of e raised to the m power, that is equal to m itself. And really, this is just a case study of the rule above it, because the rule above it said log base a of a, and if you think about it, ln natural log is just log base e of e. So we have an exponent rule you guys thought about a lot when you were younger. So a to the m times a to the n equals a to the m plus n. We have a similar rule for logs, which is that log base a of m times n equals log base a of m plus log base a of n. So similar sort of multiplication to addition rule, although the specific organization is a little bit different. We also have a division rule as well. So when we thought before of a to the m over a to the n is a to the m minus n, here we can think about this as log base a of m over n equals log base a of m minus log base a of n. And then finally, in exponents, we had the power to the power property. A to the m to the r equals a to the m times r. With logs, if we have log base a of some other value m raised to the r, that's the same thing as r times log base a of m. In other words, that r moves from the exponent to the front of the log. And you might be thinking to yourself, well, that seems a little arbitrary. I wonder why that is. And it's basically an extension of the multiplication to addition property we looked at before. Because imagine for a second, just as an example, that I had log base a of m squared. that's the same thing as log base a of m times m, just using that exponent. And then we could separate that out using our multiplication to addition property as log base a of m plus log base a of m. But then if you add those together, that's just the same thing as 2 log base a of m. And you can see here that the 2 went from the exponent to the front of the log. And that would obviously be true if the exponent was 3 or 4 or 5. You would just have more things added together, and you would end up with that coefficient in the front. So that's kind of where that property is coming from. Now, the last property doesn't really have an exponent equivalent, but it's called the change of base formula. And the change of base formula is particularly valuable for evaluating logs on calculators if you just want to use the log button, because the log button isn't specific to a base, it's just base 10. So for example, if I had log base a of m, I could rewrite that as log base 10 of m over log base 10 of a. And that's really helpful when you want to evaluate logs in base 10 and they're not in base 10 already. So these are all of our log rules, and we're going to look just briefly here at a couple examples. But before we do that, I want to talk about things to avoid. Common mistakes that I see when people misinterpret log rules. So the first one I see is that logs don't distribute, and they don't distribute over addition or multiplication. So these are things that are not true. Log base a of m plus n is not the same thing as log base a of m plus log base a of n. You can't distribute logs into addition. Similarly, it's not true that log base a of m times n is the same thing as log base a of m times log base a of n. Logs don't distribute across addition or multiplication. The final mistake I see all the time is just misinterpreting the multiplication to addition rule. Log base a of m times log base a of n is not the same thing as log base a of m plus log base a of n. The multiplication needs to be within the same log. It can't be 2 logs multiplied together, even if they share a common base. So these are just common mistakes to avoid. I want to mention them in hopes that you'll avoid making them. So let's look at a couple examples here. In the first example, I just want to look a little bit at how you might use some log properties. Now, this problem is sort of just a stylized example because we're looking at log base 2 of 4 times 16. And you could just multiply 4 times 16 and then work your way through evaluating log base 2 of 48. But I just want to show you how you could do this problem using log rules to avoid your calculator. Because we could use the addition property to think of this as log base 2 of 4 plus log base 2 of 16. And then our goal here would be to get our base to match our value inside the parentheses, because then they would cancel. So we could think of this as log base 2 of 2 squared plus log base 2 of 2 to the 4th. Because then we can move those exponents to the front and think of this as 2 log base 2 of 2 plus 4 log base 2 of 2. And you'll notice here that at this point, these both just equal 1 based on one of our properties. So our answer would just be 6. So this is just an example of how you can apply log rules to come up with the solution to a problem without a calculator pretty easily. Another common example, and you'll see this a lot on standardized tests like the ACT and SAT, so to avoid giving you a calculator, I'm going to tell you that log 5 equals 0.699 and log 15 equals 1.176. We want to figure out the value of the expression log of 3. And at first glance, this doesn't appear to be helpful at all. But if we can convert log 3 into log 15s and log 5s, then it will be helpful. So I'm going to think first of log 3 as log 15 over 5, just rewriting the 3. And then we can use our subtraction property to think of this as log 15 minus log 5. And then at that point, we can just plug in our values. Log of 15 is 1.176, minus log of 5 is 0.699. So then our answer would just be 0.477. So we can evaluate the log of 3 based on those other values, as long as we use our log properties to rewrite them. So that brings us to the end of our 8.5a video. Give the homework a try and let me know if you have questions.